the analysis of salient pole machine or power equation of salient pole machine. In this, we are going to calculate power equation also. Right. Let's check this. Here, in salient pole machine, we have D axis and Q axis. Yes or no? We have D axis and Q axis. For example, I am taking here. This is D axis and this is Q axis. I am taking like this. And for example, this is the voltage V. Of course, armature current also is there. This is my armature current IA. But actually, we should take like this. This is the current ID and this is the current IQ. This is the current ID and this is the current IQ and this is the voltage V. This is the voltage V. Voltage V, IA, but actually this is due to D axis and Q axis. This is ID and this is IQ. What is the angle between this V and IA? Is a phi. What is the angle between V and E? Actually EMF also is there. This is a Q axis actually, but this is also a EMF equation, EMF vector. So the angle between E and V is delta. E and V is delta. So I will give you with some clarity. See, this is EMF and this is D axis. Of course, this is V and this is the angle delta. Right? This is the D axis ID and this is the Q axis IQ. Of course, here IA is there. Just remember that. Not to do here. Just remember that. Right. IQ, ID and voltage V. In generally, in our machine, in salient pole machine, we have RQ and RD separately and XQ and XD separately. So now we want to draw the vector diagram. In that we have a ID RD drop and IQ RQ drop, ID XD drop and IQ XQ drop. These are the voltage drops. Let's represent in our vector diagram how it is. ID RD should be parallel to ID. So parallel to ID is equals to ID RD. And next, ID RD completed. IQ RQ. IQ RQ should be parallel to IQ. Always the resistive drop in parallel to current. So in parallel to current. So this is parallel to IQ. This is IQ RQ. And next, IDXD. IDXD should be perpendicular to ID. This is ID and its perpendicular value. Its perpendicular value. So this is what IDXD. This is what IDXD. Of course, you remember just this is a Q axis. Just remember. So IDXD also completed. Next, IQXQ. IQXQ should be perpendicular to IQ. So perpendicular to IQ. That's why this is IQXQ. So now tell me, what is the EMF? E is equals to V plus IDRD plus IQRQ plus or minus IDXD plus or minus IQXQ. This is our EMF equation of salient pole machine. This is the vector diagram for that. Is it okay? Now, generally, see here, for example, I am some simplifying. This is what IQ, and this is what IQRQ, and this is what IDXD. Now, what is the direct answer for this EMF? The direct answer for this EMF, E is equals to IQ plus, IQ plus IQRQ plus or minus IDXD. This is also the EMF equation, equal. These both are same. Sir, of course both are same, but once observe the second equation carefully. This is in terms of voltage. This is the voltage drop. This is the voltage drop. What is this? This is a current. The equation is a blunder. It should not be like this. This is also should be in terms of voltage. So now make it in terms of voltage. IQ in terms of voltage. How? Take this triangle. Take this triangle. This is a 90 degrees right angle. So from this we want adjacent. We want adjacent of delta. So IQ we want. This is the adjacent, right? Adjacent nothing but cos delta. Cos theta is equals to adjacent upon hypotenuse. Adjacent upon hypotenuse. From this IQ is equals to V cos delta plus IQRQ plus or minus IDXT. This is the EMF equation of salient pole machine, which is very important one. Based on this, they asked already 2 times in GATE exam. Now also we can expect question on this one, right? So this is the IQ is, we can written as V cos delta. Then what it can be written as? For this, take the sine delta. Sine delta is nothing but opposite upon hypotenuse. Opposite nothing but ID upon V, nothing but here ID is equals to V sine delta. ID is equals to, what is the value, sir? V sine delta. IQ is the V cos delta. Voltage component along D axis, voltage component along Q axis. So we got it. Here IQ is equals to V cos delta and ID is equals to V sine delta. This is a V cos delta and this is V sine delta. You should remember these two. And also I said you already, for example, this is EMF and this is ID and this is IQ. For example, some armature current IA is there. Armature current IA is there. Nothing but like this. For example, this is some IA. What is the angle between these two? The angle between these two is nothing but xi. The angle between EMF and the current is xi. From this again, what is IQ from this? From this also, IQ is equals to IA cos xi will come, because adjacent, that's why cos theta, and this is opposite, that's why ID is equals to IA sin xi. You should remember these two. Here the angle between these two is the phi. So xi is equals to delta plus or minus phi. We already discussed just now. Xi is equals to delta plus or minus phi. Plus for lagging and minus for leading. We know this is equation already. Right? So you should remember all these things. This is the analysis of salient pole synchronous machine for lagging load. Now the analysis completed. Now let's go for power equation. Of salient pole meshing. Now we have to go for power equation. Before that, we calculated this one. Now, before going to power equation, here we have a small assumption. What is that small assumption? If armature resistance is neglected. What I am saying that? If armature resistance is neglected. I neglected my armature resistance. If armature resistance neglected nothing but RQ 0 and RD is also 0. If RQ 0 nothing but IQ RQ drop is nothing. If RD is 0 nothing but ID RD drop also nothing. These two are nothing, sir. So we have to assumption of RA is 0. For this assumption, what is EMF equation and what is the vector diagram? In this vector diagram, this is neglected and this is neglected. We have only this one and this one. And here also this is neglected. And remaining everything is same. We can take the vector diagram for this assumption and derive the EMF equation for this assumption. Sir, why here the armature resistance is neglected? Because the drop due to armature resistance is very small. That's why I have to neglected this very small drop content RA. Is it okay? So neglect this and redraw this diagram. Redraw this diagram. Are you ready? Right? So redraw here. For example, I am removing this total and I will draw again. See. Again, this is the EMF and this is the D axis. Of course, this is Q axis. Of course, here we have a voltage V. Of course, this is Q axis, actually IQ, and this is D axis, actually ID. But voltage component along the Q axis is V cos delta. Voltage component along the D axis is V sin delta. We know this already. Now let's represent the drop. How? IDRD neglected, IQRQ neglected. The next IDXD. So the next IDXD. This is what? IDXD. And next IQXQ. IQXQ perpendicular to IQ. This is what? IQXQ. So this is same. IDXD. Now what is E? These two neglected. Actually E is equal to V plus or minus IDXD and plus or minus IQXQ actually. But now E is equals to IQ plus or minus IDXD. IQ plus or minus IDXD. That's it. IQ plus or minus IDXD. But what is IQ? IQ nothing but V cos delta. So what is the EMF equation for this assumption? Now tell me the EMF equation. E is equals to V cos delta plus or minus IDXD. Actually this is the EMF equation with assumption armature resistance neglected. Are you okay? But for example, I am taking lagging load, then this is only plus, then this is only plus. Okay, so from this I want ID. So calculate ID. E minus V cos delta is equals to IDXD. Then ID is equals to E minus V cos delta upon XD. This is what? The current component along the D axis. That is the current component along the D axis. Now I want current component along the Q axis. Can you anyone give me the answer? Anyone is there, intelligent fellows? Tell me the answer. I will give you chocolate for this answer. Tell me the answer. I will give you chocolate. Okay, tell me the answer. From this graph, you have to give the answer. Okay? Are you getting or not? So let's see. See, this is V cos delta, V sin delta. This V sin delta is equals to IQ XQ. What is that? V sin delta is equals to IQ XQ. Yes or no? Then IQ is equals to V sin delta upon XQ. This is the current component along the Q axis. What we have here? One is the current component along the D axis, E minus V cos delta upon XD is a one equation. And the current component along the Q axis, so IQ is equals to V sin delta upon XQ. This is another equation. And voltage component along the Q axis, voltage component along the D axis. These four are very important for power equation. To find the power equation of salient pole synchronous machine, now our final aim is that only. Let's go for power equation. Are you ready? Are you ready? So let's derive that power. The power developed by salient pole synchronous machine is equals to the power of D axis and power of Q axis. What is the power of D axis? Voltage component and current component. Voltage component and current component. Like this. So tell me, the power developed by my machine is equals to voltage component along the D axis. Along the D axis, voltage component is V sin delta. And the current component along the D axis. The current component along the D axis is E minus V cos delta upon XD. The next, voltage component along the Q axis, nothing but V cos delta, and current component along the Q axis, current component V sin delta upon XQ. This is what the power developed by the salient pole alternator. But we have to make it simplified for easy understanding, for easy remembering. So how we can simplify? The power developed by my machine is equals to EV upon XD sin delta, is it okay? Minus V square upon XD sin delta and cos delta plus V square upon XQ sin delta and cos delta. Then what is the answer? What is the next step? EV upon XD of sin delta plus V square sin delta cos delta, I took a common. If these two taken common, what is the answer? 1 by XQ minus 1 by XD. This is the answer. So multiply and divides with 2. 2 sin theta cos theta is equals to sin 2 theta. You know this formula. So now tell me, what is the power developed by my synchronous alternator salient pole machine? EV upon XD sin delta plus V square by 2. 2 sin theta cos theta is nothing but sin 2 theta and 1 by XQ minus 1 by XD. This is our power developed by my salient pole synchronous machine. Very, 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 very important thing is this. Are you okay? Right? Here, the power developed by the synchronous machine having two parts. So, we have to analyze these two parts now. Right? Right? So what is the power developed by my salient pole alternator? Power developed is equals to EV upon XD sine delta plus V square by 2 sine 2 delta 1 by x cube minus 1 by xd. This is the total power developed by my machine. Right? See here, we have a two parts. I said you already, I told you already. This is and this is. This is called electromagnetic and this is called reluctance. Reluctance power and electromagnetic power. Because, for example, if excitation 0, when excitation 0, EMF also 0. When EMF 0, the power developed by the machine is equals to 0 plus, because here EMF 0, this value 0. 0 plus V square by 2 sine 2 delta 1 by x cube minus 1 by xd. This is value 0 because excitation 0. That's why this is called electromagnetic power. And this is even though in salient pole machine, even though excitation removed or excitation 0, it will develop some power. It will develop power is called reluctance power. What is that power? It is called reluctance power, and this is the electromagnetic power. When excitation removed, the power is 0. Electromagnetic power, the power is remains is called reluctance power, and that machine, excitation removed synchronous machine, is called reluctance machine, which works due to reluctance torque. Even though excitation removed, nothing but in reluctance machine also NR is equals to NS. Reluctance machine also rotates at synchronous speed. Our reluctance machine, of course, excitation is 0. Then how it will rotate at synchronous speed? For example, like this, we have a pulse, right? And here the excitation is removed. This is open circuited, and my armature is developing the power actually, but excitation removed. Then how it will develop the reluctance torque? The reluctance torque is due to only air gap, and for that the magnetic fields are produced by observing the reactive power from the bus bar. When excitation is removed, the machine absorbs the reactive power from the bus bar in order to make the poles, and due to these poles, the rotor also rotates at constant synchronous speed. So reluctance motor also rotates at synchronous speed. There is no any changes. This is about the reluctance power and the electromagnetic power. Sir, if excitation removed, how much power will develop out of 100%? But out of 100%, it will develop only 15 to 20% of power only. Remaining 80 to 85% of power is 0, that is electromagnetic power. Now they will ask you a question. In power equation, at what angle we can get the maximum electromagnetic power? At what angle we can get the maximum value of this power? Can you tell me? Yeah, when delta is equals to 90 degrees, the electromagnetic power is maximum, is very important. And when this is maximum, if delta is equals to, actually this total should be 90, when delta 45, this total is 90. So the reluctance power is maximum when delta is equals to 45 degrees, and reluctance torque also maximum. This is 2017 or 18 gate question. 2017 a recently gate question. So the reluctance torque also maximum when delta is equals to 45 degrees. Okay sir, reluctance power maximum at 45 degrees and electromagnetic power maximum at 90 degrees. Then the total power developed by my synchronous machine, when we can get the maximum value. The total power maximum when delta is equals to, tell me, option A 90, option B 45, option C 0, option D in between 45 and 90. For that, let's draw the load angle power curve or power load angle curve. Okay, I am going to draw power load angle curve. Power and what is that? Very good. Load angle, P and delta curve. So see here, I am taking power on x-axis and power versus load angle, right? So load angle on y-axis. This is the power developed by my machine. First draw for electromagnetic power. If delta is equals to 0, this value 0. If delta is equals to 90 degrees, this is maximum. When delta is equals to 90 degrees, this is maximum. When delta is equals to 180 degrees, this is again 0. So the curve is like this. How it is? Let's see carefully. So for example, if here is 90 degrees, so we can get the maximum power at 90 degrees. This is electromagnetic power, is a sinusoidal wave. And when it will be maximum at delta is equals to 0, this is also 0 because 2 0 0 sine 0 0. At delta equals to 90, 90 to 180 sine 180 0. But at delta is equals to 45, 90, so at delta is equals to 45 degrees. This is the maximum. So the curve is like this. This is the reluctance power. This is the reluctance power. This is the electromagnetic power. So what about total power? When these two are here increasing and here power also increasing. But here subtraction started. That's why this is also subtracted. So this is the total power developed by my machine. This total power. This is the electromagnetic power and this is the reluctance power, but this is the total power where it is maximum. The power developed by the machine is maximum. Actually reluctance power maximum at 45, electromagnetic power maximum at 90, but the total power maximum at 60 to 70 degrees. Where we can get the maximum power? 60 to 70 degrees in between we can get the maximum power. So here, one electromagnetic power, next reluctance power, next the total power developed by the machine. Here options they given 90 degrees, 45 degrees, 60 to 70 degrees, 30 to 40 degrees. Stability, very important one. They will ask you question, when we can get the maximum stability. Right. The electromagnetic power maximum at delta is equals to 90 degrees. Reluctance power maximum at delta equals to 45 degrees. And the total power is maximum at 60 to 70 degrees. But the stability maximum at 30 to 40 degrees. Because here this is linear before 40 and this is also linear mostly. So combinedly this is linear. When we have a linear curve, this gives us more stability. So the stability is also maximum at 30 to 40 degrees. This is the salient pole synchronous machine power equation.